Welcome back to the third and last part of our workshop on digital rock physics in GEODIC 2021. The topic is digital special core analysis, or in other words, two-phase flow. First, we will compute a digital mercury intrusion capillary pressure curve, a digital MICP. Then we continue with the drainage computation. And finally, we will have a look at settings for computation of the relative permeability and resistivity index, both based on the result of our previous drainage computation. Before we do so, we start again the macro recording, now for the digital special core analysis. Please keep in mind to extend and adjust the recorded workflows according to your needs. The macros do not yet cover all of the GEODIC capabilities for digital rock analysis. So let's get back to GEODIC now. Let's continue with our workshop on digital rock physics. So first of all, for this last session, we want to start macro recording again. So please go into GEODIC. From the menu bar, choose macro, and in the macro menu, select Start Macro Recording. So start macro recording from the macro menu. And here please choose a new file name. So for example, please just exchange routine with special. So we will now start recording of our DRP workshop for digital rock analysis special. All right. Now we can see that the macro is in the recording state. And the first thing we want to record is the MICP GeoApp. So please go in the GEODIC menu bar to the GeoApp menu. And there, please choose the last point. So click SATODICT in the GeoApp menu. In the SATODICT GeoApp, there's a lot of, there's exactly 4 different GeoApps. So hysteresis, which lets you perform alternating cycles of drainage and imbibition, the mercury intrusion capillary pressure, which you want to use now, and even further things to discover for yourself. So please click mercury intrusion capillary pressure. And have a look at the options by clicking Edit. Though as you do, you don't have to set anything because everything is preset with default values for a typical digital MICP experiment. So you can change the name if you want to, and you can also see that you may use the dynamic pore morphology method for that one. However, we don't want to execute this now because it takes longer than our standard method for MICP computation. Okay, so just click OK, leave it as a default, and run and record our MICP GeoApp. While it is running, you can see plotted the saturation versus the capillary pressure. And as you see, the pressure is increasing continuously, while the saturation decreases. So, as you can see from the remaining time, an MICP computation in a digital rock at a size of 256 voxels in each direction is pretty fast. So typically faster than any lab experiment. You can also expand here the window to see if there are coming some messages from GEODIC. Okay, so it has only taken roughly 1 minute in order to compute the MICP result. So let's just move on to the plots tab in the result viewer. And here you can see the pressure in PSI units plotted with the saturation of the wetting phase. You can adjust the plot according to your needs. So for example, you can change the pressure unit to Pascal if that's what you are using in your house, in your company. Okay, you can also change the phase saturation from wetting to non-wetting if you want to. And if you click apply, all of this will be stored in your macro. So every result that you will produce will have the according units that you want to have. You can also change the appearance of the plot. If you right click into the plot and click edit plot settings. So just to show you, you can use for the y-axis for the capillary pressure also a logarithmic scale if you want to. You can just check it and apply, and you will see a different representation with more detail on the pressure steps. You can also deactivate it again. This is kind of up to you. So if you want to compare the digital MICP experiment with a lab experiment, then you will have to change the reference volume from pore space to total sample volume. So please change this here. And this is necessary in order to account for any unresolved porosity in your digital rock sample. So depending on the structure you're looking at and depending from the voxel resolution, you might have some unresolved porosity in the geometry. And you will have, or you will want to, account for this by choosing a proper reference volume. This is also highlighted in publications of Saxena et al. From 2019. Okay, having done that, we will look now at a drainage computation. So therefore, please go back to the geodetic menu bar, open the predict menu, and click the SATODICT module. So click SATODICT from the predict menu. In the SATODICT region, at the left side, you can click the drop-down menu where you find the capillary pressure curve, which we will use in order to compute the fluid distribution over drainage, but you can also find the relative permeability and the resistivity index amongst others. So please leave it at capillary pressure curve and click edit to change the wetting parameters. So what we now see here is a namely like MICP result. So we have now all the settings from the MICP stored here. So we'll have to change it according to our drainage. Okay, let's change the name to drainage result. In the experiment, you can choose either drainage or imbibition. Of course, you want to have a drainage. In that case, the invading fluid must be connected to a reservoir, as it always has to be in a reservoir rock computation. And the replaced fluid can leave a residual. This is, of course, true for applications in the oil and gas industry, so we want to click this, of course. Then you have the option to use the dynamic pore morphology method, which you can try on your own after the workshop. You can use it to compute a non-monotonic capillary pressure curve, for example, giving you the option to have smaller interface steps when using the dynamic pore morphology method. So this is new with Geodetic 2021, as already shown in the presentation previously by my colleague Oliver. So let's go to the Constituent Materials tab and make sure that you uncheck the dynamic pore morphology method and check the replaced fluid can leave a residual. Okay, in the Constituent Materials tab, we have to change a lot of things. First of all, we don't have to change the contact angle mode. So the multiple contact angle mode is used for the fluid distribution, while the other angle mode is not used for the fluid distribution. It's only used for post-processing purposes. So in order to have a change in the relative permeability depending on the contact angle, you will have to use the multiple contact angle feature. Okay, the interfacial or surface tension would be more or less something like 0.03 Newton per meters. And the invading fluid should be oil. So we want to do a drainage for an oil and gas application. And the replaced fluid should be water. We have to change this here in our structure materials. So please click air fluid here under the materials and change from air to water. So back to water again, run it. And we have now oil as the non-wetting phase and water as the wetting phase, which will be replaced up to a certain residual. You can also see here the contact angle. You can set individual contact angles for the different minerals in your phase. So we can leave the wetting phase contact angle here, for example, at 40 degrees. You can choose also a lower angle, just as you wish. So let's have a look at the boundary conditions. If we want to compute a drainage computation, we want to have the non-wetting phase enter our digital rock, but we want to have it enter at one side only. This will typically be one of the Z axis, which is our flow or computation direction. Okay, so we will change all the others to wetting phase reservoir, which means that the water can leave, the water that's in our structure can leave from these boundaries so that the oil can further invade our pore space. Okay, let's just check the first 5 boundaries to wetting phase reservoir and leave one as non-wetting phase reservoir on the Z axis. Having done so, go to the solver parameters tab. So the first thing here you see is the step size. In previous Geodict editions, the step size was in pore radii. So you had to enter 0.5 previously, but now it's the pore diameter that you enter. So 1 is the minimum step size, gives you a maximum resolution of the fluid movement. Okay. The interface step size is only relevant for when using the new morphology, pore morphology method. So we don't have to change this here, it just gives the maximum step size that the fluid will advance when using the pore morphology method with a dynamic approach. Okay, we can also leave the other ones here at the default. So we click OK, and we want to compute now our drainage. So we can run and record this. So the computation is started again, and we can already see saturation of the wetting phase at 100%, of course, and the pressure increasing continuously. And at some point, when the pressure increases, the wetting phase saturation will decrease. As always, you can expand here the progress bar or get it back to normal appearance. So already the wetting phase saturation decreases only to a minor amount, and when it reaches a certain point, the steps are becoming larger. So as the computation advances, the wetting phase saturation already decreases significantly, but we see that we only have some seconds left. So on our workstation here, it takes closely 2 minutes to compute a drainage. So if you are working on a workstation with a higher power, then of course you might be faster and even finished already. Okay, now I see the results. I hope you see them too already. And in the results tab, we want to go to the plots. In the plots tab, you will see now the wetting phase saturation plotted on the x-axis and the pressure in Pascal on the y-axis, giving you the capillary pressure curve with an irreducible water saturation at somewhere around 8% of wetting phase saturation. There's also more to discover here in the result viewer. For example, you have the data visualization tab, which offers you the opportunity to load any intermediate step of your drainage computation. But even better is the Create Videos tab, where you can create a video visualizing all of the intermediate steps from 100% wetting phase saturation up to the final with the irreducible water saturation. And as you can see here, as a short schematic view, the animation will also include, next to the 3D animation, the capillary pressure curve at the corresponding state. Alright, let's go to the relative permeability computation. Therefore, we will go back to the SATODICT section that is still open here. And from the drop-down menu, we will choose relative permeability. We will click Edit here. So the first thing we will have to do is change or apply the phase distribution of the drainage that we have performed. So we click From Simulated Wetting Process and browse for our drainage result. Okay, just choose the drainage result file and open it. And you will get a preview of the capillary pressure curve. Now here was the non-wetting phase on the x-axis. So the saturation of the non-wetting phase. We can increase the number of saturation steps so that automatically points are chosen with a nice distribution across the entire axis. So you don't have to choose all of them for a correct relative permeability computation. It's just fine if you choose an intermediate number. You can also select to compute the relative permeability for wetting and non-wetting phase for this drainage result. If we go to the constituent materials tab now, we can observe the materials that were used, so water and oil. So that's perfectly fine, we don't want to change this at all. Okay, go further to the boundary conditions. There you can choose the computation direction, which is of course set, which is always the computation direction in GeoDict. So the boundary conditions in flow direction show here again, as we have done for the absolute permeability, a periodic boundary condition with inlet and outlet, or an inflow and outflow region as defined here. Okay, though that's fine. So we can have a look at the solver. So by default, the simple FFT solver is now set here. We of course want to have the Lear solver, which is your choice number one for oil and gas applications. You can leave the error bound at a high accuracy of 99% or an error of 1% as set here. We can see this one checked, stop relative to fully saturated permeability. This option dramatically reduces the overall runtime, as the tool tip says, and yes, that's what it does. You can also have a look at the user guide for the SATODICT module by clicking the Help button here. So you will get more information on all the parameters. Also important is to have the Analyze Geometry checked here. So if there's no connection for any of the steps in the relative permeability computation, this is already found before any computation is started. Okay, we can leave the parameters at the default. Click OK and record our settings. So please click Record, not Run and Record, because this would take some time. That would go beyond the scope of this workshop. Okay, please click Record here. And now, as it says, the command is successfully recorded as macro, and no results are calculated yet. Please keep in mind that you can execute the macro after the workshop, computing everything that we are now recording. Next thing we want to have a look at is the resistivity index, which is also a typical feature to compute for reservoir applications. So we'll have to set the same things now here in this wetting parameters tab. So again, click from simulated wetting process. So we'll get the phase distribution from our drainage computation. So we will browse for the drainage result and click open again. Again, we might want to increase the saturation step numbers. So we will be fine with 7 again. Then we go to the next step, the constituent materials, and here we now have to change something. So we need some electrical conductivity in at least one of the materials. So for example, in water. So water typically now has values from our database, material database, and it is without defined electrical conductivity. So the most simple thing is to just change here the water to brine. So brine is water with a higher salinity. If you change this, we can see that we now get an electrical conductivity in our wetting phase. That's perfectly fine. We can also set a conductivity for the oil phase or our solid phases, so that it can be computed with this approach here. So one thing to notice here, if you have materials from our database without an electrical conductivity, you can just change them by doing a manual material out of them and enabling you to set an electrical conductivity. So we will just go with brine as the only phase with the conductivity. Okay, so please click boundary conditions for the next step. So here you always want to have Dirichlet boundary conditions for the electrical flux, which is most suitable for reservoir rocks. Commutation direction, again set direction. And in the solver, we don't have the Lear solver here available right now, so we can go with the tolerance settings. So the default is quite usable here, quite usable. So perfect. And we click record to save our settings for the resistivity index computation. Click record. Okay, perfectly successfully recorded as macro. So we have done all the steps that were planned for this Digital Rock Physics workshop. And now we want to stop macro recording, and we can again get our macro into the GeoApp section. Okay, so let's go back to our workshop directory, typically located in Documents and my first geodetic project if we are on Windows. And here we can just copy the DRP workshop DRA special Python macro file. Okay, now we have to change to our installation directory, Geodetic 2021, therein the GeoApp folder, and therein the DRP workshop folder that we've created in the previous workshop part. And here we want to paste our special workshop macro. So basically that's it. We can check it by opening a new geodetic. Just right click here into this taskbar icon and start another geodetic. Go to the GeoApp section, and here we already find our DRP workshop folder again, with now the routine and the special analysis. So perfect. You have everything available that you need in order to compute resistivity and relative permeability after the workshop with the settings that we've just applied. Okay, so the next thing would be to go back to the slides. It is also important to know how to perform computations in an entire core sample. So please treat this core sample workflow as an additional training for your time after the workshop. When having a segmented CT scan of a core sample, you may reproduce experimental conditions and simulate the permeability according to the lab setup. Therefore, it is important to define the region surrounding your core with a unique material ID. We have already done so for the workshop geometry, but you may also use the GATT-Geo module to create a cylindrical mask as flow cell material, as shown here in red. If you compute the permeability for a core sample surrounded by a flow cell material, you must convert the resulting permeability. So basically, the computed permeability is the sum of the core permeability and the flow cell material permeability, both weighted by their volume fraction. So since the flow cell material permeability is 0, you must divide the computed permeability by the core volume fraction to receive the permeability for the core. And this is as easy as shown here. Just look up the volume fraction of the flow cell material from the Statistics tab. Calculate the core volume fraction as shown, and finally determine the core permeability. So that's it for our workshop on Digital Core Analysis with Geodik 2021. We hope you enjoyed the workshop and want to test more Geodik features with the remaining time of your workshop license. Of course, there's still a lot more to discover, and we still have time for some questions, so feel free to ask any of yours now, and thank you for your attention.